For this video, we are going to be looking at something called biconditional statements, and these are some statements you probably ran into in that last set of in-class activities. So first we're going to define what a biconditional statement is, and that is actually a statement that contains the phrase if and only if, and we'll see how that works in a little bit. We will show that proving a biconditional statement is logically equivalent to proving two conditional statements, which turns out to be a little bit easier than proving the biconditional statement directly. And then we'll do an example proof. Alright, so a biconditional statement is a statement of the form P if and only if Q, where P and Q are both statements. Right, so it's another one of those statements that's made out of other statements. So in symbols you have P and Q with a double pointed arrow between them. So what this particular statement means is it's true when P and Q both have the same truth value. Either they're both true or both false, and then they are false otherwise. So here's what the truth table looks like. Notice that on the top and bottom row you get true because both P and Q are true, or both P and Q are false. And the middle two, where one of them is true and one of them is false, they're P if and only if Q is false. Now, it is usually very difficult to prove biconditional statements directly, so we usually have to use an equivalent form, and rather than trying to explore our way to the equivalent form, I'll just give it to you right now. The equivalent form is if P then Q, and Q if Q then P. So we, in order to have the biconditional statement, you prove two conditional statements. The statement P implies Q, and its converse, Q implies P. And just to show you that the truth table works, if we look at that third column, that P implies Q, remember that is going to be false precisely when P is true and Q is false, and it's going to be true otherwise. Q implies P is going to be false precisely when Q is true and P is false. That's going to be in that third row, right? And then P implies Q and Q implies P is going to happen anytime you have both of those conditional statements true. So that's on the top and on the bottom. And when one of them's false, then those are the middle two, and those are going to be false. And then notice that, again, you have true on the top and the bottom and false in the middle, just like we did for P if and only if Q. All right, so what this tells us is if we want to prove a biconditional statement, that actually means we can get there by proving two conditional statements. That yes, that means we have to do two proofs, if P then Q, and the statement if Q then P. Yeah, and as I mentioned, we have to do two proofs to prove one biconditional statement. So let's see how this works on an example. So suppose we have an integer n. We have n is even if and only if n plus 3 is odd. Probably something that you're not surprised is true, but we're going to show how to use our if and only if logical equivalence to figure it out. So for our proof, I'm just going to go directly to the formal proof. You can work out the details on scratch paper if you like. But what we're going to do is, first of all, be nice to our reader. Let them know what we're going to assume, what we're going to prove, and that we're going to actually have to prove two different proofs, right? So what we're going to tell them is say, look, to prove this theorem, we must prove both if n is even, then n plus 3 is odd, and if n plus 3 is odd, then n is even, so that they know exactly what they're up against. So we're going to start with that first part of the proof. We're going to begin by assuming n is even, and then showing that n plus 3 is odd. That's proving that first conditional statement. So since n is even, we use the definition of even to get that n is equal to 2k for some integer k. And then we want to figure out what n plus 3 is. We're going to add 3 to both sides of that equation. N plus 3 is 2k plus 3. Then we're going to do a little bit of algebra magic to make it look like an odd number. Split up the 3 into 2 plus 1. Factor out the 2 from both the first two terms to get 2 times the quantity k plus 1 plus 1. Now it's starting to look like an odd number. We note that k plus 1 is an integer by closure, and so it follows that n plus 3 is odd. Now we're going to go the other direction. For the last part of the theorem, we assume that n plus 3 is odd and show that n is even. Again, alerting the reader to the fact that, oh yeah, there's a second part of this proof that we have to do. Here's what we assume for that. Here's what we have to show for that. So n plus 3 is odd. We use the definition of odd numbers to get n plus 3 is equal to 2k plus 1. And then we want to know what n is. Well, in order to get n from n plus 3, you have to subtract 3. So n is equal to n plus 3 minus 3. Sort of like a simplification, but for our proof. All right. Now we know that n plus 3 is equal to 2k plus 1, so we substitute that in. And then 2k plus 1 minus 3, if we simplify that, gives us 2k minus 2. Then we factor out a 2 to get 2 times the quantity k minus 1. Then we use closure properties. We know that k minus 1 is an integer by closure, and so it follows that n is even, which is what we wanted to show. That completes the proof. All right, so now that you've seen a biconditional proof in action, now you can go back to some of those activities from the proof by contrapositive, and then move on to the other two that I have for you in the PDF file included with this video.